So I've gone over both derivatives and integrals in their basic numeric form, where you're just calculating it and not trying to do the more advanced math that we'll be getting into very soon once I teach you about limits. And I've mentioned successive approximation, which is how you get as precise a result as you want for your derivative or your integral. This is just a demonstration of it, so it's a little more clear in your mind. So let's start with the derivative. You're looking for the derivative at point P. Remember that the function is valid from a to b, and P and Q are within a and b. So P is the point you're interested in, and Q is your approximation factor. The closer Q gets to P without equaling, because you don't want to equal it, but the closer Q gets to P, the more accurate you're going to get. So here, I have a function. This line here, this red line, is x over 3 squared. It's a nice parabola. And here I have P and Q. So P is this point over here. If I move P, I'm moving where I'm interested in taking the derivative. So this would be 0. I want the derivative here, or at a negative point, or at a positive point. And then Q is the other point, how close to P I'm getting. So if I have P over here, which is the left point, and I drag Q closer and closer and closer, so Q is this point, the closer it gets to P, the more accurate the derivative becomes. And of course, if it's equal, it disappears because it's invalid because you're dividing by 0. But if we go just one tick off, you can see this is a really good derivative. If we go P at 0, the derivative at 0, then I can bring the point closer and closer and closer, and when it's almost at 0, we can see it's almost a horizontal line. And the same if I have a P over on the right side and bring it almost to P but not quite, we get the nice derivative. And you just make it more and more close to P without actually reaching P for more precision. That's all it is with successive approximation for the derivative. You just go closer and closer and closer and closer and closer, and you get your value at P. This fanciness here, this extra bit, is just so that it actually plots it on the curve. This is just a line formula. I forget what this form is called, but basically it's the slope and bias. I just move one point of the line to where P is in there, but that's just for this graph. This is the actual derivative. So then we have the integral. The definite integral from P to Q is this sum, and the successive approximation here is n. So these are our rectangles, and you can have I equals 0 to n minus 1. You can have I equals 1 to n. It's just the left and right side of the rectangle. So we start at P. We have the width of the rectangle. This is the width of the rectangle times how many rectangles times the width of the rectangle. So here's your f of x, and here's your dx. So the width of the rectangle and the height of the rectangle. It's called a Riemann sum. I think it's Riemann. It might be Riemann, but I think it's Riemann. And if you have I equals 0 to n minus 1, it'll be on the left. See, the function value is taken from the left side of the rectangle. And if you do 1 to n, then it's actually the right side. And you can do the lowest value, the highest value. You can take a middle value. There's other stuff, so you could actually do not a rectangle if you wanted. But there's no reason to get this fancy. This is fun for doing math, because math is fun, but really the point is we just increase n. So here's me increasing n. More and more rectangles. So if we go down to very few rectangles, you can see there's a lot of overshoot here and undershoot here. But if I increase the rectangles, the total overshoot gets smaller, the total undershoot gets smaller. Go to a lot of rectangles, and our sum is getting more accurate because the absolute amount of overshoot and undershoot is reduced. The same if we did it from the right. And this is just changing the bounds, P and Q, of where I'm taking the start and end. As you can see here, the notation. It's just approximations, that's all it is. So this is what successive approximation is. You're either taking a point that's closer and closer and closer to another to reduce the error for a single calculation, or when you have a sum, this sum here, you're adding more and more rectangles. So each rectangle is becoming smaller. And that's it. So hopefully that was more clear in your mind. Soon we're going to get into the advanced topics. I'm going to teach you about the limit, what a limit is, how you use limits to figure out derivatives and integrals in their full mathematical form, not just trying to raw calculate. And we'll get into the really juicy stuff. Until then, I'll be seeing you.